Hi. This is Peng Wei from Nanjing University of Aeronautics and Astronautics. In this video I will introduce our work multi-label knowledge distillation. Firstly, let's talk about what multi-label learning is. Multi-label learning addresses problems where each instance is assigned with multiple class labels simultaneously. For example, as shown in this figure, an image of a street scene may be annotated with labels bus, car, and person. To learn the complex object label mapping, there is always necessity of training large models to obtain desirable performance in MLL. While the remarkable successes have been made in MLL through the training of deep neural networks, it is hard to deploy these large models on lightweight terminals such as mobile phones, under the constraint of computational resource or requirement of short inference time. To mitigate this issue, knowledge distillation is needed, which aims to improve the performance of a small network, also known as the student, by requiring the knowledge from a large network, also known as the teacher, to guide the training of the student network. Typical KD methods focus on the multi-class classification, and can be roughly divided into two categories: logits-based methods and feature-based methods. The former minimizes the difference between logits of the teacher model and the student model, while the latter distills knowledge from feature maps of intermediate layers. Although KD has been proven to be effective for improving the performance of the student network in single-label classification, it is still a challenging problem to directly extend existing KD methods to solve multi-label knowledge distillation problems. Specifically, logits-based methods often obtain the predicted probabilities based on the softmax function. This function is not suitable for MLKD, because the sum of predicted probabilities may not equal 1 in MLL. Feature-based methods often perform KD based on the feature maps of a whole image with multiple semantics, which makes the model focus on the major objects while neglect minor objects. For example, in this figure, Vanilla and Review KD wrongly focused on the bus when the model queried the label car. Such a phenomenon would cause the model to obtain suboptimal, even undesirable distillation performance. In this paper, we use a classification model consisting of three components: a visual backbone F, a label-wise embedding encoder G, and a multi-label classifier H. Then we can get a feature map Fx for the input X, a label-wise embedding EK equals to GK Fx with respect to the number K class based on the feature map Fx, and multi-label probabilities Y hat. Here sigma denotes the sigmoid function. It is noteworthy that the used model is very general, which can be built by equipping commonly used backbones, such as residential net, with a label-wise embedding encoder. For the notations mentioned above, we use the superscripts T or S to denote the teacher or student model. For example, we use EKT and EKS to denote the label-wise embeddings for teacher and student models. This figure illustrates the distillation process of the proposed L2D framework. For a batch of training examples, we feed them into the teacher or student model to obtain the label-wise embeddings and predicted probabilities. In order to train the student model, besides the BCE loss, we design the following two distillation losses. First, multi-label logits distillation loss LMLD to exploit informative semantic knowledge compressed in the logits. Second, label-wise embedding distillation loss LLED to leverage structural information for enhancing the distinctiveness of learned feature representations. Multi-label logits distillation loss decomposes the original multi-label task into multiple binary classification problems and minimizes the divergence between the binary predicted probabilities of two models. Formally, the MLD loss can be formulated as follows. Square bracket is an operator used to concatenate two scalars into a vector, and KL is the KL divergence. The MLD loss aims to improve the performance of student model by sufficiently exploiting informative knowledge from logits. The knowledge distilled from the teacher model by only using the MLD loss would be insufficient to train a student model with desirable performance due to the limited information carried by the logits. To further strengthen the effectiveness of distillation, we design the label-wise embedding distillation loss, which aims to explore the structural knowledge from label-wise embeddings. The main idea is to capture two types of structural relations among label-wise embeddings. First, class-aware label-wise embedding distillation loss, which captures the structural relation between any two intraclass label-wise embeddings from different examples. Second, instance-aware label-wise embedding distillation loss, which models the structural relation between any two interclass label-wise embeddings from the same example. Here we use Euclid distance to measure the distances between label-wise embeddings and minimize Huber loss to align the student with the teacher. What is more, it is worth to note that we only consider the structural relation between any two valid label-wise embeddings, which means the embeddings with respect to positive labels. This is because only positive label embeddings carry specific semantic information in multi-label learning. For example, a positive label embedding of class dog indicates the presence of a dog in the image, while a negative label embedding of class dog does not correspond to any specific object, such as a cat or any other object. To sum up, firstly, we propose a general framework called MLKD. To our best knowledge, the framework is the first study specially designed for knowledge distillation in the multi-label learning scenario. Secondly, we propose a new approach for MLKD called L2D. It performs multi-label logits distillation and label-wise embedding distillation simultaneously. The former provides informative semantic knowledge while the latter encourages the student model to learn more distinctive feature representations. Thank you for your listening.